Welcome back everyone. Let's solve this question, shoe shuffling. I'll quickly summarize the question for you. You have a class of students and they decided to shuffle their shoes among themselves. Here important thing is a pair of shoes is inseparable. That is considered as a single object. So specifically we have n students in the class and we are given an array S in non-decreasing order. So non-decreasing order is something like ascending order, but it can have duplicates, right? And we are given this array S and Si is the shoe size of the ith student. And they have defined a valid shuffling. A shuffling is valid if and only if no students get their own shoes and every student gets shoes of size greater than or equal to their size. So what you have to output is you have to output a permutation, right? Like the shuffling should be represented by a permutation. So what is a permutation? I guess you might be knowing it because you have discussed this permutation part in a lot of times in 800 and 900 questions. So permutation is nothing. It's just an array consisting of n distinct integers from 1 to n in any arbitrary order, right? So here the shuffling needs to be represented by permutation in a way that ith student gets the shoes of pith student, right? So whatever permutation you output, in that the ith student will get the shoes of pith student. And of course, pi should not be equal to I, right? Because no student should get their own shoes. So that's one thing. So the question is simple. What they have given is they have given n and si. So si is the size of shoes for a given student. And what we want to output is we want to output a valid shuffling, and that shuffling should be represented by a permutation. How? ith student. So you want to output a permutation array of n integers from 1 to n in any order, and ith student will get the pair of pith student, and of course I should not be equal to pi for obvious reason because the student cannot get his own shoes. But if a valid shuffling does not exist, you have to print -1, right? So I guess the question is clear. First, like looking at the constraints, it seems as if n log n is the maximum that you can go. Now it's a good sanity check to keep an idea about the upper bound of this problem, so don't think about random approaches, right? So yeah, n log n is the maximum that you can go. Now what observations can you make here? Firstly, now first obvious observation was that how are you going to assign pairs, right? Because no student should get his own shoes. He has to get a, like he can get a shoe of the same size that he has or greater than it, but he cannot get his own shoe. Okay, let's just consider a case where all the shoe sizes are distinct. So in that case, what shoes should a student get? So I've just taken a small example here. Let's say these are the three sizes we have, 7, 10, 12. Now, if you have all the unique, let's say shoe sizes, then what should be the shoe that is like shoe that student should get? Now, this is obvious that he should get a shoe size just greater than it, right? Because if you give, let's say 12 to this 7, then what will this 10 do? This 10 will have nothing, right? So I'm not concretizing anything, but just making some initial observation. So if you want to assign a pair, like assign a shoe to a student, you will have to pick just greater than equals to it, right? So if you want to assign, if you want to give a shoe to some student, it should be just greater than it, right? So if there was a 7 here, you are better off picking this 7 instead of this. It's a little bit vague, but it's a good starting point. Pick a pair to give a student just greater than it. Okay, what next? So one thing that comes to my mind is what happens if we have just unique shoes, right? Unique shoe sizes, then what is going to happen? So let's take an example here. Let's say we have 7, 10, 15, 17, 20, something like this. So if you have just unique shoe sizes, you'll try to give 10 to this 7, 15 to this 10, 17 to this 15, and 20 to this 17. But what will this 20 do? This 20 is at a problem, right? So this 20 will have no option but to take 7. If you take, so it seems as if all the shoe sizes being unique is creating a problem. So what is the problem here? This smallest shoe size is being assigned to the student with the largest shoe size, right? So that is a problem. If I can do something that this 7 is not assigned to the largest, like the student with having the largest shoe size, my job is done. How can I do it? Can I introduce one more smaller shoe size? So you will give this student, like student with shoe size 6 is 7, but the same problem will repeat. Now this 6 will go to 20. So that doesn't seem to be working. This won't work. Can I include the student with the same size? Then this 7 will become, then this 7 will come here. But now you cannot assign, like the same problem will happen for this 7. Again, the student with the smallest shoe size will go to 20. So yeah, that is a problem. You cannot have it. So what is happening here is with the strategy that we have employed, like the smallest shoe size is always getting spared. And this is not going to solve by including a even smaller shoe size because the same problem will happen. If somehow I can make sure that the smallest shoe size is not spared, then this student with the largest shoe size will not get it. right? So how can we solve it? Like, you can solve it if somehow this group, right, this is a group of the smallest shoe size, they have a shuffling among themselves, right? A simple shuffling can be, let's say you had some more sevens. A simple shuffling can be, you give this 7 to this, so let's come from back. You give this 7 to this 7 to this, and this 7 to this. If I can have this simple shuffling, now this is just cyclically rotating by one sort of a shuffling, right? I just rotated the array cyclically by one and assigned the respective shoes. If I can have this, I can make sure that this 7 won't escape, right? So what I'm trying to say here is, guys, uh, take this 7. So I'll need to have one more 7 here, right? So I'll give this 7 to this and this 7 to this. Now what will this make sure is, the smallest shoe size will not escape, right? So the smallest shoe size will not escape to the student with the largest shoe size, right? So even if you had some more copies of it, this can be achieved. So give this 7 to this, give this 7 to this, and give this 7 to this, right? So there can be many more valid shuffling, but whatever this is doing is, this is making sure that the smallest shoe size doesn't escape to the largest guy. And to have that with just a single shoe with the smallest size will not suffice. To make sure that the smallest shoe size does not escape, you will need to have some copies of it. Just one copy also works, right? So that is fine. If you have some copies of the smallest shoe sizes, you can have a configuration here that this is not going to escape, right, to the student with the largest shoe size. Okay, the smallest shoe size won't escape, but now the second smallest shoe size will escape, right? Now this 10 will escape to the student having the largest shoe. What will you do? Simple. Have one more of it, right? Have one more of the second smallest shoe size. So now you can give this 10 to this, give this 10 to this. So this is not required here. Sorry. Yeah. So this will make sure. So if you have one more copy of second smallest guy, this will make sure now the second smallest doesn't escape to the largest shoe size possessing person. But now the third smallest will escape, right? You will give 20 to this, 17 to this, and who will you give this 15? Who will you give this 15? You will have no option but to give this 20. So the solution is simple. Add one more copy of this 15. So now this 15 will give here, this 15 will give here. Even if you add more copies of 15, you can have a valid shuffling, right? So the 15 will stay in itself. It will stay in its own, you can say, cozy environment and not leave to the largest shoe possessing person. Okay, that's fine. But now you give this 20 to the 17. 17, but who will you give this 17 now? Right? Who will you give this 17? You will have no option to give to 20. You have to make sure the 17 doesn't escape. So I have one more 17. Now give this 17 to this 17 to this. Right? So now 17 won't escape. But now the student itself, like who is having the largest possible shoe size, will get its own shoe. But that is also not allowed, right, in a valid shuffling. So what you will have to do is, you will have to include a copy of the largest shoe size as well. Right? So now everything is good. Give this 20 to this 20 to this. And what you have, ladies and gentlemen, in front of you is a valid shoe shuffling. But what have you done here? You have included at least one copy of every possible shoe to reach a valid shuffling. Right? Amazing, right? So what you have effectively done is effectively proved that if you have any shoe size that is unique, a valid shuffling cannot exist. We just proved it, guys. You cannot argue. Like we were just hunting for the solution, and we proved this fact that if you have any single shoe size that is unique, a valid shuffling can never exist. Right? For completion's sake, let's just take a general example and see what happens when you have a unique shoe size. If you can see it for a single unique shoe size, you can of course extend the idea to multiple shoe sizes to being unique. So let's just say this is our S array, right? The shoe sizes are given here. So what you'll do is you'll give this W's to this to this Z to this Z to A, this A to, I'm just assigning a student with a shoe greater than equals to it, right? This W will come here, this W will come here, this Y will come here, this Y will come here, this X will come here, here. The issue is this X still remains, and this X will be assigned to this student, and that is a problem, right? So this is where the problem lies. So the question is done and dusted concept wise. So what is the concept here is, if there exists a unique shoe size, if there exists a unique shoe size, a valid shuffling cannot exist and you're going to print -1. Else a valid shuffling exists and you can print that shuffling. Now how are you going to print that shuffling? Let's just take this here only. So there are various ways to approach shuffling. Like how are you going to do it? The simplest approach is, to get a valid shuffling, what you'll do is, let's just take this example itself, right? To get a valid shuffling, what you'll do is, you'll take this group of the same shoe sizes and just cyclically rotate it by 1. So let's just say this is 1, 2, 3, 4. If you just rotate it cyclically by 1, what will happen is you will have 2, 3, 4, 1. In other words, this guy will get this shoes, this guy will get this shoes, this guy will get this shoes, and this guy will get this shoes, right? Same for this. For this, let's say this is 5, 6, right? Just cyclically rotate it by 1. So this becomes 6, 5. In other words, this guy gets his shoes, this guy gets his shoes. Similarly for this, cyclically rotate it. Similarly for this, right? So this is what happens. Okay, I guess I have misspelled W here 2 times, but like you can assume these are some different characters. Okay, sorry for that, but yeah. So there are various ways to approaching it. So there can be many valid shuffling here, but the one simple approach is, you just cyclically rotate the same group of elements by 1 and your job is done. Now this is a very implementation specific thing, so I'll just write it here. Cyclically rotate same groups, like same size groups, by 1 to get the valid shoe shuffling. Of course, we'll discuss it more during the code walkthrough, but yeah, that's that about this question. I don't think I have anything much to discuss concept wise. Let's go to the code walkthrough once. Okay, guys, so this is Kathan from future. So I realized while editing this video that the video is getting a bit too long. So I've decided to split the video into 2 parts. So in this video, we have discussed the approach, right? The next video, we'll discuss implementation. The reason being, implementation for this question, I want to discuss some neat STL function that is specifically rotate and how to use it. So I don't want that explanation to be feel rushed. So yeah, that's about this video. I'll see you in the implementation part in the next video.